We're group independents and we did a pump around system. Our system is part of the Dower Drive Stream Restoration Project located in Howard County, Maryland.
The portion of the stream system that we were analyzing was the pump around practice. So left to right, we have the elevation view, then the cross-sectional view, and then a broader focus on what the pump around practice is as a whole. Basically, you use a pump and pipe system in order to pump water from upstream to downstream around the section of bed that you wish to work on. This is done because work in a bed with water going through has a tendency to not stick around very long. You also have walls at beginning and end of the section you are working on and a pump and pipe system to collect any extra water that accumulates through the center out of the bed of the river. We are presuming a perfect system, in which case the walls and pump initially stop this work, negating the need for the middle pump and pipe.
For continuity, we first had to calculate the area. For the area, we used a semi-oval equation. To calculate continuity, we first are using a volumetric flow rate that we obtained through the USGS database. So we used the volumetric flow rate and the area to calculate the velocity. And then for mass flow rate, we used the area and velocity previously calculated and the density of water to find the mass flow rate, which was 47.5 pounds mass per second.
All right, using this, we were able to do the work energy equation. So in this case, we are pumping from the stream to up on the bank. So that has atmospheric pressure at both ends. Negating that, Z1 is at the datum and V2 at the top as it goes up and then down is at 0. We have no turbine and and we are assuming no friction, which leaves just the velocity term plus the head is equal to Z2. So as H pump is what we are solving for, you sum everything up and it is equal to 20.55 feet. Using this to find the work, so mass flow rate found in the previous slide times gravity times the H of the pump gives you a work of 1.78 horsepower.
For the impulse momentum equation, in order to apply that, we first had to utilize Bernoulli's in order to find the pressure that was being acted upon within the 90-degree alvo. And within that equation, we set it up so that the elevation head, the velocity head, and the pressure head were negated at point 2, and at point 1, the velocity was negated. In addition, the total head was given by the manufacturer, and this enabled us to calculate that the pressure was 10.4 Alps per foot squared, and that allowed us to apply the impulse momentum equation, where the summation of forces is equal to your volumetric equation times your density times your delta velocities, which then would be able to be equated to the summation of the pressure and area forces acting within the system and the direction in which we want to know that the force is being acted upon. In this case, it would be the f of x and f of y. And with applying these variables, we're able to conclude that f of x was 795.5 Alps, while f of x was f of y was negative 795.88 Alps, and that then allowed us to apply the standard trigonometric identity equation, where tan theta is opposite over adjacent, and we were able to deduce that the angle of the resultant vector was negative 45 degrees. For the system knowledge and then how to optimize it, since fluid is fairly translucent, make that more very visible and apparent of exactly what is going on within the system is one way to do so. And to accomplish this, you can implement environmental safe dye within the system, which enables you to see how the fluid is flowing within it, or using transparent pipes, which allows you to visualize the water within it, and also 3D modeling, where you can manipulate all of the various variables to figure out the causality within the system.
This is also our references. Thank you for watching.